Thank you very much to the organizers for the invitation and the very nice hospitality. It's always, to me, very moving to be in India, so I really like it. And my first slide is the most important one. I would like to, of course, congratulate and express my deep affection and admiration for Deepak. It's really an honor for me to be here. So these are pieces of art, Deepak, very expensive by Anish Kapoor. So I could not buy them, of course, but they remind me a bit of your work, just part of it. So very expensive avalanches and sand piles. And thank you to you. So I'm going to tell you about macroscopic fluctuation theory and some work we did with Hiroki Moriya, graduate student of Tomohiro Sasamoto. Both of them are in Japan, in Tokyo. A recent work on which we analyzed and found a solution for the macroscopic fluctuation theory. But of course, I will take some time to get to there, to get to the formalism. And it's going to be, I hope, a bit pedagogical. But the end of the talk will be more technical if I get to it. The idea is that I would like that the picture at least is a bit clearer. So we are interested in fluctuations in systems far from equilibrium, out of equilibrium. But again, to understand, it's good to start at equilibrium. Suppose we are at thermal equilibrium in a room, and I want to understand a local density or a local energy or I want to analyze some local thermodynamic observable. So if I look at it, I'm at thermal equilibrium, I can understand fluctuations of thermodynamic observable just by inverting Boltzmann formula. And the first person who did that in 1906 was Einstein, who created the theory of thermodynamic fluctuations. So of course, the number of microscopic configurations is exceedingly maximal at thermal equilibrium, but you can always use this formula near equilibrium, expand the entropy, sorry for that, the entropy near equilibrium to second order, and this will provide you with Gaussian fluctuations of thermodynamic observable, and these Gaussian fluctuations are governed by the second derivative, by the Hessian A of the entropy. So this is for static fluctuations. But I may also be interested to measure the local density with time, and I get a time series, and I want to understand the statistics of this time series. So the next step was taken by Onsager. But to understand the statistics of time series, we need some constitutive relations that connect gradient of thermodynamic observables with local currents, typically something which is like Fourier's law, J is minus gradient of T. So this was put in a kind of general framework by Onsager and then developed during the 50s and the 60s by Kubo School and other people. And the key to understand that at near equilibrium are the fact that you write linear relations between current and gradient, local gradients of thermodynamic observables. And Onsager introduced a matrix which connects these gradients to currents. This matrix is usually called L, and L is symmetric because of underlying time reversibility of physics. So this is the famous Onsager reciprocity relations from 31. Almost 20 years later, Onsager and Mallick went one step further, where they could write some effective close to equilibrium dynamics for thermodynamic observables, which I will call X. So it's a Langevin equation, simple linear Langevin equation. X dot is LAX plus a noise. L is Onsager's matrix. A is the Hessian of the entropy. So this is a simple Einstein-Uhlenbeck type process. And one important thing to notice is that the correlation of the noise, of the Gaussian noise, is governed by, again, Onsager's matrix. And this guarantees you that static fluctuations go back to Einstein theory. So this is a Langevin process, again, close to equilibrium. It allows you to compute different time correlations between thermodynamic observables. It allows you to analyze time series near equilibrium. As soon as you have a Langevin process, if you want to make things a bit fancier, you can write a path integral automatically. So you can say that this Langevin dynamics gives a weight to trajectories, to path, to time histories, And these weights are given by a path integral, which is a Gaussian path integral. Again, the main ingredients of this path integral are Onsager's matrix L and the Hessian A of the entropy. So all this is building up, but of course it's highly non-trivial. It took half a century, but building up things at and near equilibrium. So this weight over trajectories, or this action, is also called Onsager and Markov's action principle. And the idea is that macroscopic fluctuation theory can be understood in one manner as a kind of nonlinear, far from equilibrium generalization of this kind of path integral. That's a way of understanding it for physicists. So now let's go to large deviations and MFT, macroscopic fluctuation theory. So we want to have a kind of coarse-grained understanding of non-equilibrium transport. This is a very hard problem with plenty of subtleties. I will just sweep them out and try to take a very naive approach, which happens to be exact in some cases, but not all of them. Many people here have worked and seen and know that Fourier's law, for example, is not always true, but at least naively, if I'm transporting particles from a reservoir at density ρ1 to a reservoir at density ρ2, I have a current flowing through a system. I could have also some electric field applied to the particles if they are charged. And what I can write is a conservation equation of the density, of the local density. The derivative, time derivative of density is minus the divergence of a current. And at least, yeah?
In the previous when you went.
Yes, to the action.
Jacobian is
The
Jacobian is not.
No, the Jacobian is not important here. I will take dominant paths. Yeah. And anyway, you can always say, I mean, here it's additive noise, so it's really not important. You can always say that you are in Ito and not in Stratonovich. So your Jacobian is 1. But this will, yeah, I will come back to that later, ask me again. So at least I can write a phenomenological transport equation, and the current, the local current here, it has two parts. One part is a diffusive part governed by a diffusive constant d of rho, and one part is just transport due to an external field governed by the conductivity sigma of rho. So at least I would think most of physicists would be convinced that such an equation should be generally be true, often true, and that the two transport coefficients d and sigma contain most of the physics of the system. But of course, at this level, they are purely phenomenological. If we want to compute them, we have to disentangle the microscopic dynamics of the problem. So now let's go to more mathematical models. We are interested in interacting particle systems. So we know some microscopic rules, independent particles, the exclusion process, on which I'm going to talk a lot, particles hopping on a lattice with double occupancy forbidden, more complicated process, one is called KMP. People like Paul Krapivsky, who will be arriving tonight, hopefully at last, studied more complicated processes where you can have clusters of particles and you don't allow to have more clusters forming and so on. And you can compute for many processes, not all of them, of course, the values of d and sigma, and they can become more and more complicated. For example, for the Katz-Leibowitz-Spohn process, which is a kind of Ising type, dynamical Ising type model, there are formulas for d and sigma, which are almost 1 page long. So I didn't write them. I think Yariv computed them a long time ago. Paul again, Paul. So the point is that this is perfectly deterministic. But how can we take into account fluctuations? So one way to understand why we want to understand fluctuations is that, again, if we take this picture of these reservoirs communicating to a bar, in the simplest case, we know that there will be a profile which will be linear in the case of Fourier's law, and there will be a constant current in the stationary state, but there could be local fluctuations of the current in time and space, and there could be also local fluctuations of the density profile, and we want to quantify these fluctuations. So for some classes of systems, which are called driven diffusive systems, you can convince yourself and even prove that for large systems in some scaling limit, the probability of observing some local current and some local density takes a so-called large deviation form, which is of the form of exponential minus the size of the system and some functional I, capital I, of J and rho. So this is, of course, very much similar in form to a kind of Boltzmann principle. And the goal would be, can we compute this capital I of J and rho? Can we find a principle at least to state it? Because once we have it, we somehow just know a bit more about the statistics of fluctuations far from equilibrium. So a principle to compute this I is precisely what the macroscopic fluctuation theory gives you, the MFT action. Again, this is not totally general, but this is fair enough general so that, for example, the models I showed you and many others can be encompassed by this MFT theory. So the MFT theory tells you that indeed this probability takes the form of an exponential of some action, and the action is given by a functional. Okay, it's a functional of the current and of the density. And if you look at it, well, it's in fact something that you could almost guess. And I'm going to tell you in the next slide that indeed, once you have it, it seems natural. So you could say, okay, but if it's so natural, why isn't it trivial? The thing is that the Rome group around Bertini, Gabrieli, De Sole, John Alasigno, and Landim proved this principle mathematically, rigorously, using large deviation theory for many systems. And then it was postulated for other systems and then checked by exact calculations or approximations that indeed it gives relevant and correct physical consequences. So what happens is that indeed we should compute this action for all possible J and rho, but we are often interested in the large time limit. Capital T is the time, there's no temperature here. In the large time limit of the problem. And in the large time limit, well, the saddle points of this action will dominate the probability. There will be a probability concentration. Yes?
Yeah, I was just wondering, the end conditions rho 1 and rho 2 don't come into this.
They come, but I put them, so they will come in a few seconds. I will write the Euler-Lagrange equations associated with this action, and they will come as boundary conditions, of course. Yeah. So I didn't put them in the action. Otherwise, you should put integral. It's a path integral over all rho and j, starting with rho 1, finishing with rho 2, and so on and so on. I'm a bit sloppy, but don't worry. So how can you understand that? Well, you can, in fact, understand that as going back to the hydrodynamic limit, which, by the way, was proved rigorously by these people, and especially, for example, Varadan got the Abel Prize for exact proofs of hydrodynamic limits. You can somehow phenomenologically add a noise component to the current. And if you do that, and you add a noise component to the current with an amplitude which is given by the square root of the conductivity, then precisely writing the path integral associated with this stochastic PDE gives you back the MFT action. So the MFT action can be viewed as the action associated with the stochastic Langevin heat equation, okay? Nonlinear heat or continuity equation. So let's be slightly more precise. Again, these transport coefficients, D and sigma, encode for the microscopic physics. And for the symmetric exclusion process, D is 1, best possible, and sigma is quadratic, it's rho, 2 rho, 1 minus rho. So you see, from this point of view, this appears as a very natural generalization of Onsager-Mark loop. Very similar idea. Okay, so now I'm going a bit more into the technique. We have an action. We want to find the dominant path, so we write the Euler-Lagrange equations associated with this action. So I'm not going to do it. It takes 2 pages, but it's not impossible, far from it, to do it. And you get these equations. So in principle, you get equations for J and rho. But as usual, you like to go from Euler-Lagrange to Hamilton by doing a Legendre transform. And it's much nicer to write the optimal equations in the Hamiltonian form. And you get two variables in the Hamiltonian form. Rho, the density remains rho, but the current is traded off into a kind of momentum conjugate variable, which is often called H in our community. So I still call it H. So H is not the Hamiltonian, but it's the momentum. So these are the two MFT bulk equations. I didn't put in the boundary conditions yet, but these are a set of two hydrodynamic, nonlinear coupled equations for two fields, classical fields, rho and H. And these equations come from a Hamiltonian structure. There is a Hamiltonian, and you can rewrite them in the usual Hamiltonian way. Okay, so now we have a framework. The physics is in D and sigma. If you give them to me, I can write these equations precisely. And somehow we want to dig out fluctuations in our interacting stochastic systems by solving these equations. Unfortunately, these equations, even though in principle we could use them, they contain many difficulties. They are coupled, they are nonlinear. This one has a negative sign in front of the diffusion term, so it is stiff, but just on the boundary, so it's still solvable. And boundary conditions introduce also problems. So they are difficult to solve mathematically and even numerically. People like Baruch Mirson in Israel devise some numerical recipes to compute them, and other people too. Okay, so people have been trying to analyze them by using perturbation methods, by linearizing them, or by trying to solve them in the stationary case. So this was done essentially by Derrida and Bodino already a long time ago, finding stationary solutions. But time-dependent solutions, apart from the free case, where particles don't see each other, random walkers which are independent, this you can solve. But apart from that case, exact solutions or solutions, analytic solutions of the problem were not known. And then within the last year and a half, a few solutions for related problems, optimal fluctuation paths with similar PDEs were found, one by the group of Le Dussal in Paris, one by the group of Baruch Mirson in Jerusalem, another by the group of Benichoub using totally different technique, nothing to do with MFT, and one by the group of Tokyo and Saclay that I'm going to tell you about. Okay, so before I tell you that, I need to, so this was a kind of very general part about non-equilibrium fluctuation. I need to give another piece of information that maybe everybody doesn't have. It's about scattering and inverse scattering. So this is another chapter. So suppose we are studying optics, classical optics, and we have an object with a different reflective index, or we are studying Schrödinger equation, and we have a localized potential, and we are scattering waves, and waves are scattered by this object or by this potential, and you can, and the object is localized, so far away, the waves are plane waves. So you can characterize the object by scattering wave through it and computing the reflection and transmission coefficient, okay, R of k and T of k. So this, okay, usually I don't, in our, again, community, reflection and transmission coefficients, and you can reflect from the right, from the left. So there are 4 of them, and they are called A bar, B, and B bar, which depends on the wave number k. Reciprocally, so there is a relation between the form of the object or the potential and this scattering data. Reciprocally, if you know the scattering data for all wave numbers, you can try to reconstruct the underlying object or the underlying potential. That's the inverse scattering problem, okay? So there is a kind of one-to-one correspondence between the object, the scatterer, and the scattering data at infinity. And indeed, there are some equations called the GLM, Gelfand-Levitin-Marchenko equations, that allow you to go backwards. So it's an inverse problem. Okay, that's classical optics if you want. I mean, then let's talk about something different, slightly different. Now suppose that your object is changing, or your potential is changing with time. Okay, it's with some parameter. I said time, I should not have, which I call t. So at frozen value of t, I can again do my scattering, and I get a scattering data A, K, A bar, B, B bar, which depends on this parameter t. Okay. So of course, because this, so I froze the t, and I take the scattering data. Now I'm deforming my potential, so my scattering data is moving and it's changing also. Again, there's a kind of very complicated nonlinear relation between the potential and the scattering data. But of course, if the potential moves, changes, then the scattering data changes too. Now there's a miracle that can happen sometimes. It can happen that this potential uxt has an awfully complicated dynamics, horribly complicated, that we don't really know how to follow, how to solve, but the scattering data it produces is very simple and does not evolves in a trivial way. Does not involve or just catches a phases or catches a constant. Very simple evolution for the scattering data. Then, if we know the evolution of the scattering data, which is simple, we can imagine that we can reconstruct the dynamics of the potential by inverse scattering. Okay? So this is a miracle, and it happens with probability 0. Okay? This miracle is called integrability. This is classical integrability. So it's, of course, extremely rare. And this was developed in the 70s by people who studied nonlinear wave equations, nonlinear physics, KdV, NLS, people from plasma, hydrodynamics, solitons, and many names are associated with this whole beautiful theory in mathematical physics. For example, Kruskal, Miura, Lax, Newell, Zakharov, Fadeyev, many people. They developed an absolutely pristine theory of solving some nonlinear complicated evolution for a potential U by doing inverse scattering. So this seems complicated, but there is one case we absolutely know how to do that. If we want to solve the simple linear heat equation, we go to modes. The modes evolve trivially by catching a phase, and any finite time, we reconstruct the solution by doing Fourier synthesis. So this is the same thing. This is a nonlinear Fourier transform that people do to solve some of these integrable equations. They start with the initial data, initial potential, ux at time 0. They compute the associated scattering data, AA bar, BB bar at t equal to 0. The scattering data, because the equation is integrable, evolves in a very simple manner. We are going to see it. And then by doing inverse scattering, they can reconstruct the form of the object or the potential at any finite time t. This is a principal thing. And again, in the linear case, we know that this is nothing but Fourier synthesis or eigenvalue decomposition in Schrödinger equation. And this is more than an analogy. It can be shown that this inverse scattering reduces in the linear limit to Fourier transform. Okay, so now I come to the main topic of my talk, putting things together, putting MFT together with inverse scattering for this simple exclusion process. But first I have to tell you about the problem. So we consider the infinite line with this simple exclusion process, symmetric. I'm not going to recall the definition. I hope 95% of the people know about it, particle hopping with exclusion on a line, classical particles. And I start, let's say, with two different densities with a quench, a density rho plus, high on the left, and a density rho minus, smaller, let's say, on the right. And I let my system evolve. So there will be a current going through 0, and there will be a total number of particles which have crossed 0 between time 0 and time capital T. This integrated, time-integrated current, counting statistics, I call it QT. So now, that's a very simple, purely mathematical problem studied by many mathematicians, but with some physical interest, of course, in non-equilibrium systems. There are a few ways of trying to kill this problem, to solve it. So one way, which is the hardcore way, but the very beautiful one, it would have been a subject of a different talk, it is to go to the macroscopic system and do combinatorics and use the toolbox of integrable probabilities and Bethe-Ansatz and really get solutions at any finite time and any finite position in the form of some freedom determinant. All this is possible, but this is hard. By the way, this is a whole field now, a subfield of probability theory, which is called integrable probabilities. And really, I think I'm not being how do you say that, too polite, but I sincerely think about that, that this field was opened by Deepak in a famous 4-line paper in phase transitions that Joachim Krug already alluded to it yesterday, where for the first time Deepak used better ansatz for a non-equilibrium problem to compute a dynamical exponent 3/2. So it showed that you could try to solve by better ansatz non-equilibrium dynamic problems. It was known that better ansatz can be used for spin chains, but you can solve dynamical problems, and then it developed to a whole industry, and many people work on it. Probably, maybe even Deepak would not recognize his baby if you look at what it looks like now, but it really comes from there. Okay, so this is possible, but then you get combinatorial objects, and also you lose the hydrodynamic picture. Everything is microscopic. You don't see really how to reconstruct the density field, the hydrodynamics, the evolution. So it would be much nicer to have a physical approach to this problem. So by the way, if you want to know about the microscopic approach, this is something we did with Tomohiro and Takashi Imamura a couple of years earlier. So I want to have a physical and hydrodynamic picture. So in the coarse-grained point of view, then I just say that the total current is just the integral of the density difference between time t and time 0 on the right. I count how many much more particles I have on the right at time t. And what I'm interested in is the characteristic function or the full counting statistics of this time integrated current qt. So the average of exponential lambda qt. In the long time limit, it can be proved rigorously that this behaves like exponential square root of t times some Lyapunov function mu of lambda or cumulant generating function mu of lambda. And somehow we want to understand for any given value of the fugacity parameter, which is conjugate to q, what is the value of this function, mu of lambda, and what profile creates a given current into the system. If I want to have a current which is much larger than the one which you expect to from kind of mean field analysis, naive analysis, then somehow there should be a kind of conspiracy of the whole system to create a wave that goes through the system and enhances the current that goes through it. So now you see what we should do. We want to take statistics of some observable with respect to the MFT measure, which I give you here. Okay, we have the MFT measure, and we want to compute statistics, and we shall take dominant parts. So now, in the last 7 minutes, I will try to give a glimpse of how this can be done. So we want to take dominant parts. So again, we get some Euler-Lagrange equations, which I write in the Hamiltonian form, and which I specialize to the case of the symmetric exclusion process. And then we have these famous boundary conditions you asked about, Sriram. I'm going, of course, very, very fast. And these boundary conditions come from the fact that I'm interested in the current observable. So they contain information about lambda and the fact that I'm interested in the current. I could have tagged the particle. If I tagged the particle, it would have been a bit different. I could have taken some different observables, but for this observable, I get these boundary conditions. So this is a well-defined mathematical problem. 2 PDEs with boundary conditions. Unfortunately, the boundary conditions are mixed and non-local. One at time t, one at time 0. Okay, you have to do with that. And once I'm able to compute the dominant profile, the solution of this equation, then I can reconstruct the cumulant generating function by a simple integral. So even if you don't like physics at all, I hope you do, you can look at that as a kind of purely mathematical problem that one has to solve. So this is the problem where we and other people too were stuck for a while trying to solve these MFT equations. So there are different steps. Maybe in the end I will tell you how and why. I will not tell you why. I will just tell you how. So for many, the macroscopic system is integrable. It has plenty of properties. And here you go to the macroscopic coarse grain limit, And there was some feeling among many of us that these equations should have enough structure so that they could be broken out. And indeed they have, but the problem was to break them up effectively. And one important progress came quite recently, essentially thanks to this young PhD student, Moria, when he realized that through this mapping, which looks totally awful, but has some very nice physical justification, which I may answer to question if you wish to later, but just take this for granted. If you substitute this change of variable into the previous equations, you get these very symmetric looking and nice balanced equations for two variables, u and v. So they are now very symmetric. And they are more than that. If you look at these equations and just for fun, you call u psi and v psi star, you immediately see that this is nothing but a nonlinear Schrödinger equation. And once you have NLS, you're happy because you know that there are machineries that can allow you to play with it, to solve it. So that's where this inverse scattering machinery comes out. I still have 3 minutes and a half to do inverse scattering. The idea is that these equations which are here, so you remember in inverse scattering, you have to reinterpret the unknown functions. For example, here there are two of them, u and v, as potentials in some wave equation. So I just tell you that the wave equation we're interested in is this one. It's a linear equation. In fact, it's a Dirac equation with two components, psi1 and psi2, where u and v play the role of potentials. Okay? And these equations, you have, again, Sriram's question was absolutely fundamental. The boundary conditions will be very important. So these equations, you can do scattering for these equations, and you can define scattering coefficients, A bar, B and B bar. But the problem is, what are you scattering? I mean, you need to know something about u and v, either at initial time or at final time, to start the scattering process, to implement it. And here also we have been lucky. This awful looking change of variables transforms the initial condition into very nice looking initial problem. In fact, by this change of variables, what's going on? You should subtract the time that I'm losing now. Exactly. No, don't talk about that. No. No, I'm just, getting out of depression. So, no. You have to subtract the time also. No World Cup. No, we won it. We won it, Laetitia. Okay. So the boundary conditions are in fact delta functions. So you end up having to solve Schrödinger Dirac type equations with Dirac equation with Dirac function, Dirac distribution like potentials. Solving a Schrödinger equation with a Dirac potential is easy. You have just to do some pasting. You can give it to your students if you forgot how to do it. And this can be done explicitly. Okay, I'm putting many things under the carpet because in fact there are two boundary conditions. There's some matching thing to do. But in the end, what we get using inverse scattering, we get the fact that these U functions, which represent the profile, U is a profile. There are some Fourier transform on positive side and negative side. They satisfy a very nice equation, which is in fact a Riemann-Hilbert equation. The product of the Fourier transform on the upper plane by the Fourier transform in the lower plane is 1 plus a Gaussian. And this can be solved by using Cauchy formula. So in the end, we are able to disentangle entirely the MFT problem for ZEP and get not only equations, but also pictures, which is more interesting for the hydrodynamic of the problem and for the density profiles. For example, if I start with the density profile, rho plus on the left, on the right, and rho minus on the left, and I want to create some extra current into my system. I want to push more particles than I wanted to. So then I have to use the fact that the initial density can overshoot at initial time. So I have a kind of a wave which is developing. I'm sorry, I don't know how to make pictures. It would have been nice to have a picture with time dependent. So this is the initial overshoot. You have this soliton of current which travels through the system. And in the end, you have an undershoot of density profile. Okay, so I think I more or less managed to convey the message. The message is that computing large deviations out of equilibrium or MFT solutions is a challenging problem which interests quite a few people in our community. Many progress were made at microscopic scales using matrix ansatz, beta ansatz, combinatorics, integrable probability. But this is very technological, very arcane. And a more hydrodynamic picture based on PDEs, which are kind of more bread and butter for normal physicists, was welcome. And at least in principle, this was given by this macroscopic fluctuation theory action, but the equation that resulted from them looked a bit unsolvable. But fortunately, they are solvable by using this now quite ancient method of soliton theory and inverse scattering, which was developed in nonlinear physics and hydrodynamics in the 70s, but which by miracle, it's not totally a miracle. I may tell you that in a second, but by kind of miracle also applies to these non-equilibrium, some of these non-equilibrium stochastic interacting particle systems. So quite a few groups hit on that during the last 18 months. And we, in fact, hope that the inverse scattering method, maybe not as much as the beta ansatz, but it could open a new pathway to understand non-equilibrium systems at the hydrodynamic level and to solve these MFT equations in different geometries for different particle systems and so on. Thank you very much for your attention.
Thank you, Kirone, for a very nice talk. Questions? Hi. Sorry, maybe this is a very naive question, but can I, if you go back to the PDs on U and V, maybe I'm just confused about something. So U and V are real functions, right? U and V are real functions. So so this mapping, so you're saying this coupled PD is integrable coupled PD?
Yeah.
But then you make this connection with NLS. So, I mean, how do you? So
No. So Manas, your question is not naive at all. The I was a nightmare during literally 2 years for Tomohiro and myself. So this is just a kind of analogy. This is to convince you that this looks like NLS, but this is imaginary time NLS. And you cannot, in fact, you cannot exactly use the technology developed for NLS to solve this weak rotated. But fortunately, there exists a machinery, a slightly extension of NLS, which is called, in fact, AKNS, Abrowitz, Knaup, Newell, Ségur equations, which contains NLS, but which contains also this imaginary time and more complicated equations than that. And using this formalism, you can solve this one. So in fact, this I did the last time this morning, maybe I should not, but this is a way to try to convince you by putting things under the carpet, but that these equations are nice, but the fact that the I is missing is very important and non-trivial. Yariv?
Very clear. So can you make this opaque transformation more plausible?
Yes, thank you, Deepak. So this is something I prepared during lunchtime. I don't know if it's visible. Is it visible? Okay. So this opaque transformation has a long history. So here you have the exclusion process, symmetric or asymmetric. You have particles which are jumping on a lattice. Okay. On that side, you have the Heisenberg spin chain, which is a quantum model, XXX or XXZ. So it was understood by Deepak that the asymmetric exclusion process is nothing but the Heisenberg XXZ model. So here these are Pauli matrices, sigma, hat. And in fact, we discovered that even earlier, Shlomo Alexander had realized that the symmetric case But he was not interested at all in counting, in computing dynamical, it's true anyway, dynamical exponent. In the symmetric case, symmetric cropping, the single file problem is exactly the Heisenberg better Hamiltonian XXX. So there is a mapping like that, which gave rise to the whole development of integrable probability for stochastic interacting processes. So now I have this. I go to the coarse grain or hydrodynamic limit, and I get Langevin equation. I take saddle path, I get MFT. So that's a coarse grain limit. So now I forget about particles, and I have a local density, and I have the equation that I wrote to you. Okay. On the other side, I have the Heisenberg spin chain. And so these are Pauli matrices on a lattice, C2 everywhere. And if I take a kind of coarse grain procedure, I get a spin with a very large spin, 1/2 plus 1/2 plus 1/2, and it becomes a classical spin. So because of a Heisenberg Hamiltonian, I can write Heisenberg equation of evolution for any observable. A dot is I Lie bracket of A and H. And then I can take a classical limit by replacing I Lie bracket by Poisson bracket and take a continuous limit. And then you get something which is in fact quite classical, which is called the Landau-Lifshitz, not Ginzburg, Gilbert equation, which represents a classical spin of norm 1, let's say on a line, with magnetic interaction. And this is this equation, dTds. This is a classical spin on the sphere, on the real space, is the Laplacian of S vector by S. These are vectors, okay? So this is the classical Landau-Lifshitz Gilbert equation. Now, a long time ago, people from Russia, I think, Tarkanian, but also Lakshmanan in India, they realized that this Landau-Lifshitz-Gilbert equation could be mapped to NLS using a very beautiful geometric transformation of curves on the sphere, etc., with the I manas, precisely, with the I. Okay, so that's NLS, I don't remember the sign. So the idea was, okay, we have this correspondence at microscopic level. Is there something, once we do the coarse graining on the left goes to MFT, coarse graining on the right goes to NLS or Landau-Ginzburg. So this mapping between MFT and classical spins was known. In fact, it was found by Roche a long time ago, but it was a small remark somewhere, and also by Bernard Derrida and Antoine Gershenfeld. But again, it was an appendix, and it was a kind of cute remark, but not, I would say, implemented to an extreme. It was just that, okay, MFT is this equation. The problem is, and that's why your question was so important, if you do this transformation, the boundary conditions become completely off. They become non-local. It's a nightmare. Okay. So now you have this Lakshmanan transformation, which goes from LLG to NLS. So there should be an arrow from here to here that should somehow do this work. Okay. But composing these two things is a nightmare again. But the transformation that I showed you is exactly doing that. It's going directly from here to here. And the boundary conditions are well transformed. So that's the logic behind it. But this is, of course, reconstructed a posteriori.
So you might have answered it now, but does the fact that the microscopic model is integrable guarantee that the MFT equations are?
No, so this was a kind of wishful thinking, which happened to be true. It does not guarantee, because when you do coarse graining, you lose many things. You lose conserved quantities, but hopefully yes, and even better than that. What we think is that even, suppose you have an equation, that's a case of KMP, which is integrable at macroscopic level. But KMP, the microscopic model, is not integrable. But there should be a microscopic model which has the same coarse grain limit, which is integrable. And indeed, there is one. So the precise understanding of the micro integrability, the process, and so on, is not clear, but it's a kind of guiding principle.
question. Yeah.
I have a question. Suppose I have a microscopic model for which I can write the MFT equation, say SSCP. Can I see or extract what does this conjugate momentum field correspond to in my microscopic dynamics?
That's a very good question. I think quite a few people have thought also about it and have their kind of answer. I don't think there's a very clean answer, but the thing is that we want to understand anomalous fluctuations, large deviations in the system. So somehow we are conditioning the system to some current. And we want to understand how it behaves macroscopically to create this current. Okay? So when we condition a system like those we are looking at, technically this is called the Donsker-Varadhan tilting and so on. What happens is that somehow to create an extra current, it is as if you're adding some local electric field, some local asymmetry. Even though your initial system is symmetric, to create an extra positive current, the particles behave under this conditioning as if they were asymmetric. So this extra field, the gradient of this field, this extra field, if you want, plays a role of a local dynamically generated potential that creates the rare fluctuations you're interested in. So you can understand this extra field as an extra potential, or the gradient of H as an extra electric field. It's a kind of asymmetry which is dynamically generated for your particle to do something that you want you to. Somehow in your evolution to get a rare event, you're only selecting some evolutions. You know, if I start with Brownian motion and I want it to finish here, I'm selecting only the trajectories which are going from here to here. So somehow, quote unquote, but you can put this in a precise way, you're almost creating an attractive potential at the final point. You're catching your Brownian particle. So that's what it's doing here. You're creating some dynamical field that creates that provokes the current you're interested in.
Thank you.
There's a question.
Hi, Christian. Where is he?
So, can I ask a question?
Of course.
So I was wondering, I mean, this question can also be asked when you're in equilibrium, right? How you generate a particular density profile for current, but I couldn't quite understand how the bulk equations feel the boundary conditions where the two densities are the same at the edge. What is there really a simplification, or is there a problem as difficult in equilibrium as in non-equilibrium?
No, it simplifies a lot, and this was really analyzed. I mean, simple, but not so simple. So it was analyzed in different point of views, and the one I like the most is the one by Roré, Julien Tailleur and Vivien Lecomte, and Roré Courchan, where they showed that in fact, if you have equilibrium, in fact, they even showed that you can transform your problem in some cases to map it to equilibrium, but not always. If you have equilibrium on both ends, there is an extra property which is time reversal that occurs because equilibrium is time reversal symmetric. And then you can find solutions of these equations, analytical solutions, which are time reversed of natural solutions of your, okay, let's say it in another way. You have this action, Christian, okay? And in this action, you have some trivial solutions, which are because the action is a square. The action is a square. I'm going the wrong way. Okay, the action is a square. So there are some trivial solutions, which is just J equal to minus D gradient rho. These are trivial minimas because it's a positive, okay? So these are just somehow the natural downflowing solutions of the MFT, but I mean, they are not the ones solving our problem with our boundary conditions. But in the case of equilibrium, Roré et al. Showed that indeed the time reversed solutions of these equations, which are the natural flowing down equations, are the ones who allow you to solve the problem at equilibrium. So they were able to reconstruct the density profile fluctuations that had been computed before by Derrida, Leibovitz, and Speer using the matrix ansatz by precisely using
I
this idea.
understand, but my question was more, if you look to the final equations in NLS, do you see there the simplification?
So I didn't
Or
try,
is
but
it
I'm
close
quite
to
sure,
equilibrium?
yes.
Is there an expansion parameter?
Yes, no, but I think so. Yes, I think so. I think that essentially you will have some conjugate property between U and V, and this you'll be able to solve it. You see, there is one trivial solution, which is V equal to 0, and U is the trivial flow. U is just the trivial solution of the heat equation, if V equal to 0. So it's not that one, but it's another one which is conjugate to that one. So yes, you can do that. I'm not
Okay.
precise enough. I need to sit and think for a while.
Yeah, I mean,
but-
it's also the question is in what sense the non-locality disappears close to equilibrium, because there must be some non-locality here, right, in the profile?
So
Just like you
the-
have in the Derrida solution or the Derrida-Leibovitz-Spear solution for the
You're
free energy,
perfectly right.
non-equilibrium free energy.
So the non-locality is in the large deviation function,
But
but
not
the profiles, but not in the profiles. The optimal profiles are still local. The optimal field H is local, but then in the end, when you substitute them and you want to compute the large deviation functional, then it's non-local.
Okay. Okay, thank you. Thanks a lot.
I have a question about so this miracle with the simplification of the scattering coefficients. Does this apply generically to any kind of integrable system? Because I'm also thinking about, for example,
No,
the systems. Okay.
I would take it as a definition.
What?
As a system is classically integrable
Yeah.
if precisely the scattering data evolves in a nice way.
Oh, okay.
So quantum integrability
Yeah.
is related to this Young-Baxter
Yeah.
condition. Classical integrability
Yeah.
is related to something which is called a Lax pair.
Yes.
And in fact, a Lax pair exists for this MFT equation, for NLS, for KDV. So the existence of a Lax pair,
Yeah.
which is the same as having a simple evolution of the scattering data, can be taken as a definition of classical.
So could this method be
integrability.
applied to the examples shown by Herbert Spohn at the beginning?
So Toda chain is integrable.
Yeah.
But always, I mean, I'm just coming back to Sriram's remark, the devil is in the detail.
Hmm.
For example, we are trying to solve the same bulk equations, but different boundary conditions, and we are stuck on that for the last 9 months. We still hope that we'll be able to do that, but you never know. Little change can spoil everything. That's the point.
Okay, so let's thank Kiran
Thank you very much.
for the mission.